All right, recording is rolling. Welcome to Thursday, September 21st. All right, I have a few points of school news, and then yeah, you guys have your laptops, which is awesome because we're going to do Kahoot on mostly in Newton's first law of motion. Do you guys happen to remember? This goes a while back. I handed you guys a packet about a week or two back. Has like these slides on the back, and then there's 3 pages of conceptual questions. The first page is the same Kahoot questions that we're going to do today. So if you wanted a paper to follow along, you can read the questions. And then might have a few spare minutes at the end of class so I can knock out some of those textbook puzzles with you guys. All right, first thing. Tomorrow's going to be a different kind of day. We've got this reunification drill. So tell you guys as best I can tell you what's going to be going on. This is a new thing. Never done anything like. I don't know if this is coming from the state or from the district. Right here, guys, everybody focus here. So you know what's going on tomorrow. Right. So tomorrow, right. Here's best I know what's going on. Is you go to your first period class, right? First period teacher takes attendance, and then probably somewhere like 5 or 10 minutes in the class, they're going to make this announcement for this reunification drill. I think the purpose of this has to do something like if there was something crazy like a school shooting or something like that, they could figure out how to navigate everybody and reunify you with your parents. Hence reunification. So, maybe your teachers earlier today told you where you're supposed to go. Who knows? Who knows where you're supposed to? Yeah, to the gym, right? To the gym. So everybody's going to be in the gym. Right. Now, your first period teacher probably will not escort you. Maybe, but probably not, because all the teachers have assignments. There's different places we're supposed to be. I know I personally am supposed to be like in the bus loop back here, right? So anyway, you're going to make your way to the gym, and all the students are going to be in the gym at the same time. Okay. Right. Yeah. Try to plan for school shooting, but right then, I don't know how much this is relevant to you guys exactly, but maybe nice to know. We've got all these different locations with all these different things going on. The main one you guys care about is student staging area. Students are funneled into the gym bleachers. Teacher monitors are posted in front of exits. Bathrooms are unlocked. Right, so guys to those if you need them. Right. Your parents are supposed to be coming in through the auditorium. Oh, ID cards. Guys, are you guys bringing your ID cards to school every day? You're supposed to. And are you definitely going to bring them tomorrow? Yeah. All right. So something to do with checking ID cards. Now this is some kind of trial run. I imagine they're going to check your ID cards at some point as part of the process. Oh yeah. Did you have a physical card? I would bring that tomorrow. Yeah, that's probably the best way to go. All right. And then what else is going on here? Oh, the reunification area looks like a front office, like building 1, I guess, something like that. All right, so yes, you guys are in the gym, parents coming through the auditorium, reunify the front office, something like that. All right. And then, all right, okay, so there you go, reunification. Hey, you guys good with reunification? All right. Next thing. Download Blue Book onto your school laptop. So here's email that all the teachers got. Tell every student to download this program called Blue Book onto your school laptop. So you're supposed to go to collegeboard.org. Now, some of you guys might already have an account. How many of you guys are taking an AP class? Oh, okay. If you just raise your hand, then you already have an account, right? Maybe you don't, right? And if you don't, then you can create an account, and you can download this Blue Book app, right? Now, let me switch over because I'm trying to make this convenient for you guys. So let me point out exactly where you can see this. All right. Well, we switch over to honors, although it's not super different. But here we go. All right, honors. All right. Here's all the stuff we've been posting. Hey, look, we got all our class videos posted. Yay. Oh, hey, what is this? It's the last thing I posted last night. Download Blue Book link. Oh, look, collegeboard.org. Create an account if you need to. Download the Blue Book app. Guys, know your College Board login information, because that'd be convenient, right? So you don't have to like do a password reset the whole thing, right? Now, there's 2 upcoming applications for this Blue Book. One is that the school will be conducting a hey, get back here. Right. The school is conducting a digital readiness test on Monday. I think how it's working out is in your first period class, I don't know 100% sure, but this is my best guess what's going to happen, is on Monday in first period, they're probably going to make an announcement and have everybody turn on their laptops at the same time and make sure that everyone can access Blue Book, right? The other application is this PSAT that's coming up, which mostly applies to 10th graders, but there are some juniors and seniors that are taking it too. So they're trying to move away from paper pencil tests and make it all digital, just on your laptop. So the PSAT is going to be all through that Blue Book. Okay. All right. So you guys know where to find that, what to do. Did you guys write in your planners to go download Blue Book onto your laptops? Right, so you guys got that? All right. Let's switch back over here. All right. Next thing. Teacher of the Year. So every year I get one of these ballots in my mailbox. Here we go for Teacher of the Year. Now, I've never had any of these teachers as teachers, but you guys have. So what I always do is I always pull all my students, all my classes, who would be the best person for Teacher of the Year. I will check one of these boxes and then submit this form. Right? But this is also a really good opportunity where I can teach you guys about voting systems, because depending on what rules you have for voting systems, there's different voting environments, there's different election dynamics, and sometimes even different outcomes. So I want to teach you guys about what's called first past the post voting system, and we're going to contrast that with something called ranked choice voting. Which actually there's different subcategories. There's different ways you can process ranked choice votes. We're going to focus on a simple one that's called instant runoff, right? Which is really just one subcategory, right? Now there are other kinds of voting systems too, but I just want to focus on these two today, just to get you guys think about what are election dynamics, how does this work? What are different types of systems, right? All right, so here we go. We got 8 candidates. Now, is everybody looking up there? Because I'm about to see show hands and get votes for these candidates, right? Does everybody see like someone they really want to vote for, right? As like a #1 choice? Okay, right. So hopefully you do, right? Because it's about to get a vote count here in a few minutes. Right, now, give you guys some directions here. Now, depending on what election system you have, there could actually be different outcomes, and that's been happening pretty consistently today. Right? So if it doesn't happen here, maybe I'll pull up some past ballots from earlier today and show you guys how that might happen. Right? But I want you guys to vote for who you really, really want to be Teacher of the Year, regardless of how everybody else votes. So for example, suppose, for example, you really like Miss Barnhill. You're like, oh, Miss Barnhill should totally be Teacher of the Year. But, oh man, I think I might be the only student who's voting for Miss Barnhill. And that might be a wasted vote, because maybe there's a really close race between Velasquez and O'Boyle, for example. And maybe I have an opinion between those two. I have a preference. And if I vote on one of those two, well, I can't be voting for Miss Barnhill. If I vote for Miss Barnhill, maybe I'm like throwing my vote, and it could be more useful over here. Right? I don't want you guys to worry about that at all, and you guys will see why. So we'll go through this process, and then I'll tell you how these different processes work out, different systems. Right? So vote for who you want, regardless of who anybody else is voting. Okay, you guys that? Right? And everybody gets one vote. One vote. Here we go. Right. So who's voting for Miss Barnhill? Miss Barnhill got 1, 2. There's 2 votes. 2 votes on Barnhill. Who's voting for Contreras? Contreras. Who's voting for Monroe? Monroe. Okay. Vote for Moreland. Moreland. 1, 2, 3, 4. 4 votes on Moreland. Velasquez. Velasquez. Okay. Let's vote for O'Boyle. O'Boyle. What's on O'Boyle? Dravies. Vote for Dravies. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that 9 votes on Dravies? Okay. And Wayne. He's voting for Wayne. 1, 2, 3, 4. Right, 4 votes on Wayne. Okay. Yeah, I think it's gonna work out pretty interesting. All right, so question for you guys. Out of that list of candidates, who has the majority?
No one.
No one. That's the right answer. No one has the majority. Because what's the definition of majority? More than half, right? Nobody has the majority. Mr. Dravies has the what? Plurality, right? That's the most number of votes, right? This system right here, first past the post, does anybody know what that is? What was the criterion to win this type of race? Yep. not only that, just actually, yeah, it's kind of a deceptive name. All it is just most votes. So if you had a first past the post system, Mr. Davis would win, and then that would be the end of the election, right? Now, there's some problems with that if you think about the dynamics of how that works out, right? So let me just give you guys a for instance. Right? Suppose you're voting for candidates for a public office. Now, if you're doing like a public office vote, normally it's not just personalities you're voting for. Normally these candidates come attached to like platforms and ideologies, right? What if, just for instance, Mr. Dravies had like some particular platform that he was promoting, right? And all these other candidates had a platform that was like on the opposite end of the spectrum. They were all kind of close to each other, but were definitely opposite of Mr. Davies. Well, you see how the dynamics would work out is that they effectively like split the vote, and if they all got together, they would have the majority among them, right? But if they're all running at the same time, so you would get like a minority winner, and then it could be the case that like everyone else collectively would for someone else, right? So there are different solutions to that, right? Oh, I meant to mention a couple of terms. I meant to mention something called spoiler effect. Spoiler effect, right? For example, what if it was just Dravius versus Wayne, for example, and it could have been like 10-9. I'm just making something up, right? I don't know if it's gonna work out that way, right? But then Barnhill joins the race, right? And it's like splits the vote, and then Mr. Dravius wins just because there's like more candidates going on. So Dravius would be like the spoiler in that case, right? It also says something called strategic voting, right? Where you as a voter are now no longer voting for your preference. Now you're voting, based on how everyone else is voting. Like, well, how's the whole herd voting? Maybe I just have to kind of vote for them, just so that I get like the less of two bad options kind of thing, right? Right. Okay, so there are different solutions. We're going to look at one particular solution that involves ranking your choices. So what if instead of just checking one box on the ballot, what if you get to rank your preferences? Say, well, I like this candidate first, but here's my second choice and my third choice. Right? If there's like 8 candidates, maybe you just care about those 3, and then you just stop ranking when you stop caring, right? Well, what happens then is that it effectively initiates like a primary type process, and whoever had the least number of votes gets eliminated. But then their votes aren't just like thrown away; it's kicked over to their second preference, and then possibly third preference if that matters. So I'm going to definitely eliminate all the 0 candidates. Right? We're going to have to toss out Sparnhill, didn't have enough votes. Right? Now at this point, there's a race. Well, let's do a 3-way race. We might do several iterations possibly, right? And this process would continue until there is a majority, right? Like a true majority. Now the voters don't have to keep going back to the ballot box. They only go one time. They just rank their votes, and then the system, like a computer system, that takes over from there. Right. So we're gonna have a like a second iteration. Right. You guys ready for that? You guys ready? Right. So your options are Moreland, Dravies, or Wayne. Okay. That's all you get to choose. Okay. Right. So show of hands. How many guys vote for Moreland? Moreland. Let's vote for Moreland. Got 1, 2, 3, 4. Right. 4. Okay. Okay. Same as before. Okay. Who's voting for Dravies? Dravies. Got 1, 2, 3, 4, 5, 6, 7. Hold your hands up. Right. If you vote for Dravies, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there are 9. There are 9. Okay. Right. Votes for Wayne. Just vote for Wayne. 1, 2, 3, 4, 5, 6, 6. Okay. At this point, does anybody have the majority? No. But we do have Wayne beating Moreland. Okay, and here's where like different processes. There's different ways you can. We just did an instant runoff process. Right? It is possible that Moreland might beat Dravies at the end. There's something called like Condorcet winner. I'm not gonna get to that today. But what we got is a race now between Dravies and Wayne. Okay, so we're gonna do Dravies versus Wayne. Right, so here's the last vote. Here's for the win. Show hands for Dravies. Show hands for Dravies. Dravies. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9? Right. Votes for Wayne. Who's voting for Wayne? Wayne votes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh. All right. Maybe there's a lost vote because somebody didn't carry either way. That's all right. Right. So in this case, it looks like a tie. Sometimes that'll happen with like small classes, right? But you guys see in principle, could have been either one of them. But like, whoever the non-voter was, he could have voted for either one, right? And then maybe Dravies would have won under a first past the post, of course, right? But it would have been close between those two with this different type of voting system, right? Guys, that. Right. And then this system will get rid of the spoiler effect. You don't have to worry about strategic voting, anything like that, right? So it's like a better tech system. Okay. All right. I've been asking all my students today, who's learned this at all in any of their social studies classes? You guys learned this at all? No? No? Okay. So that's what they've been saying all day. So, well, learn it here. There you go. You can learn about that. All right. All right. You guys ready for Kahoot? Kahoot. All right. Let's switch over to Kahoot. I'm gonna get fired up right here. Kahoot time. All right, recording resumed. Oh, look, you guys go. All right, we got a party. Physics party. Galileo found rolling a ball down one inclined plane. It could roll how far up another inclined plane? What do you guys think? Sure. All right. And so most of you guys got that. That is awesome if you did. Retrospect, I don't know exactly how this ended up on this Kahoot. It's more of an energy question, but anyway, that's how it's just. So suppose you got like a half pipe type shape, right? Let a ball roll down. It can roll up to that original height. In reality, usually there's a little bit short of that because of frictional losses. But it definitely can't roll above that unless you give it a push or something. All right. All right, back over here. I still got points on the board. Points on the board. There we go. Ooh, it's a close race. Wall of inertia. All right. Object rest, a rest. Object in motion will maintain its velocity unless there's an outside force acting on it. All the above. It's all true parts. I got Harper, MLX Oak, Stump Player, Isaac, Logan. Law of inertia applies to. There you go. Moving and non-moving objects. Right. All right. After firing a cannonball into frictionless space, how much force to keep it going? Aha! Look at you guys go. Oh, man. Well, I'm flipping my screen just because I was going to anyway, although I'm assuming we got that. Right. Here. All right. So you guys remember my classic example over on this page is Voyager spacecraft? Or how about this one right here? Right? Constant velocity, no forces, no forces. It's just going because of inertia. It's just going. Hey, go. Force of gravity suddenly stop acting on the planets. What would they do? Oh, look at you guys. Look at you guys. I'm going to switch over just for the recording. But yeah, you guys got it. If there's a planet orbiting the sun and gravity turns off, bam, right there. Yeah, it just keeps going in a straight line. Right? There's a law of inertia right there. Hey, what if we change this up a bit? What if we have like a ball and a string? ball on a string, and whip it around horizontal circle. Soup, 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 soup. Right, now take some scissors and right there. Does the ball make a random 90-degree turn and fly straight away? No. Does the ball keep going on a straight line path? Yeah. There you go. There you go. Just like that. Oh man, you guys are doing so well though. Yeah. Oh, okay. But yeah, should have been. Yeah, I'll go back and check that. Yeah. What's that? Okay, so yeah, let me flip over here and do a little bit of review with you guys. A little bit of review. All right, so I got a question on the last one. Would say so the wording on the answer to the one with the planet was if the gravity turned off, it would fly off at a path that's tangent to its orbit. This is tangent to its orbit. All right, so if you like hold a roller flush to this orbit, like bam, it's a straight line path. Just like it's going. Right. What is inertia? What is inertia? Inertia is like resistance to change in motion. So look at these two guys. Right now, there's 1 kilogram mass. Am I feeling anything to do with its weight? No. If I pick it up, now I feel its weight. But if I do this, guys, what if I do this on the moon? Is it equally difficult to do this on the moon? Yes, it is. What if I'm up in like floating around in deep space? And we're going boom, boom, boom. Is it equally difficult to do this in space? Yes, it is. Yeah, because I'm feeling because this has like 1 kilogram of inertia. This one is smaller. Ooh, is it easier to do this? Yeah, it's easier to change state of motion because it has half the mass, half the inertia. It's twice as easy to accelerate. Right? There you go. There's inertia. Right? Or here, flip back over here. So right now we're just using mass as a measure of inertia. When we get to December, the location of that mass can affect its rotational dynamics. But for now, mass is a measure of inertia. So like Newton's second law of motion, F equals ma. The more massive, the more difficult it is to accelerate. Right? Right. I've also got a fine Paul Hewitt for you guys. Here we go. Right. What do we have down here, gang? No staples, no Velcro. Is there a when you're by yourself? Right. And if one of those was a milk carton, hey, that'd be the answer to that one right there. Milk carton has inertia. Inertia. Tendency to just stay put. Tendency to do what it's doing. All right. Got Stuck Player, JP, Logan, and also Isaac. One object has twice as much mass as another object, which means it also has twice as much. Inertia, right? So if you put the same force on it, on those objects, the object with twice the mass would accelerate half as much. Maybe that's a second law application. Compared to its weight on Earth, a 10 kilogram object on the moon. Guys, weight is a gravitational force, right? Gravitational force. How does that change? Yeah, there you go. Would weigh less on the moon. Okay. Less gravitational force, way less on the moon. Isaac on fire. Compared to its mass on Earth, the mass of 10 kilograms on the moon. Ooh, mass, inertia, mass. Same mass, right? Same mass, different weights. You guys get that concept? All right. The mass of a sheep that weighs 110 newtons. Oh, nice, nice. And you guys are knocking this out of the park. All right. All right, so let's get you and get that. Right. You guys remember, guys, right. Remember I've been writing M times G for weight, mass times gravity field. Right. So if you know the weight, you can get the mass by just dividing by G. Or alternatively, if you know the mass, you can get the weight by multiplying by G. Right? G on Earth is about 10 meters per second squared. Okay. All right. Whoops. Whoops. That's hey. Oh, my Zoom's doing something weird. No, come on, share screen. Okay, here we go. All right, we're gonna be all right. 15 newtons, 45 newtons, opposite directions. What's the net force? Net force. Yeah, 30 newtons. All right, let me draw that out. You guys can see that. I can do that with some force vectors here. Suppose I got 45 newtons to the right. 45 newtons of pushing to the right. If someone else comes across and pushes 15 newtons to the left, you guys see if you connect those tip to tail, 45 to the right, 15 to the left, you get this resultant, which is like 30 newtons, right? 45 versus 15 gives results in 30. Oh, yeah.
Wouldn't it be like in total though, like all around 60 newtons?
If it was the same direction, it's like here. If I got a soccer ball in the middle of the field and I got two kids, and one kid kicks it 45 newtons to the east, and the other kid kicks it 15 newtons to the west at the same time, right? That ball's going to accelerate as if there was a single 30 newton force acting on it, right? And if you know the mass of the ball, you can take 30 newtons divided by the mass, so you can say it's going to accelerate to the right at that, right? Force divided by mass. Yeah, there you go. Yeah. Right. Now, if they were kicking in the same direction, then you would add those forces together. All right. Oh, whoops. Okay. You would have the largest mass of gold if your gold weighed 1 newton. Where? What 1 newton of weight? But different amounts of mass. Which one's the most mass? Where's the most gold? Ooh. All right. That's a pretty tough one. Let's go why. All right. So, hey guys, everyone focus here. Everyone focus here. It's a pretty tough question. I got the moon, the Earth, and the Jupiter. So I got 3 different scales, right? And they're all reading 1 newton. So let's start with Earth, like the Goldilocks, right? So here's like actually, this is 1 newton. 100 grams weighs almost exactly 1 newton. So 1 newton right there, bam, right? Now if I go to the moon and that scale's also reading 1 newton, isn't that like a huge mass resulting also in 1 newton? And then you go to Jupiter, and so little tiny mass results in also 1 newton. Here's the most gold right here, right? You guys got that? Yeah, because huge gravity field on Jupiter. All right, how are we doing on points? We got Isaac, Tristan, M. Alex Soph, Jumbo Josh, Harper, Equilibrium. Yeah. Yeah, there you go. The net force is 0, of course. If you break those into components, horizontally, vertically, that's still true. Right. Now, we haven't actually talked about the gold one yet. The gold one we'll get to in like December. It's like a turning moment. That'll also be true. All right. I got Amora, Tristan, Isaac, and Alex Silf, and Harper on fire. 500 newtons. What's the tension in each strand of rope? Nice, nice. All right, here's where I've got an extension question for you guys. All right, so this is what you're given. Right, this guy's hanging right in the middle, weighs 500 newtons. He's equilibrium. There must be 500 newtons total upward, so 250, 250. Right, that makes sense, right? Right. What if this guy wasn't hanging right in the middle? What if he's taking like 90% over to the right? Right. Do you guys still think it's 250, 250? Well, it has to add up to 500, right? To balance out this 500 down. Right. Do you think that, guys, as this guy scoots over to the right, what do you think is happening to the tension on the right? Right. Do you think it might look possibly something more like this, like 450 and 50, still balances out the 500 down, right? So it's still equilibrium, right? But how would you know exactly? Well, it probably depends where he's located, right? Right. So we don't actually have enough physics at this point in the class to answer this. You need to bring in something called torque. Who's ever used a wrench? Who's ever used a wrench? Guys use a wrench, right? Or how about anytime you open this door? Are you applying some force at some distance? Right? So that's called torque. We'll talk about that in December. You can use that to figure this out exactly. What's the force in each rope going to be? But if he's right in the middle, then you can say, okay, it's going to split half and half. All right. Then the sum of the forces goes to 0. It's the important point. All right. Harper's still in the lead. Friction always acts. How? Opposite of the motion. Okay, friction's always trying to slow everything down. Opposite of the motion. All right, Ariel, Tristan, Amora, and Alex Harper. Maximum possible resultant of 3 newtons and 4 newtons. Yeah, 7, right? Because guys, if you push in the same direction, 3 and 4 together can add up to 7. Right? Guys, what if they're here, guys? Follow-up question. Guys, everybody, look up here. What if they're opposite of each other? What's 3 and 4 opposite of each other? Would be 1 newton, right? What if they're right angles to each other? Right angles. What's 3 and 4 make at right angles? 5. How'd you know 5? It's a Pythagorean triplet, right? Right? Use Pythagorean theorem if they're right angles. All right. We got Jumbo Josh on fire. Yeah, Alex Silv, Stunkler, Harper, Tristan moving back to the top. What's the tension on the clothesline? All right. This one's a little tricky. Okay, let's go by. You guys remember spring scales lab? You guys remember doing this right here with the spring scales? Right? The answer is actually embedded in this poster. Because whatever the weight is, let's suppose the weight's like 100 newtons, right? Weight's 100 newtons. Right? Now, if your spring scales were exactly vertical, what would the spring scale rating be in each one? 50-50, right? Be 50 here and 50 here. Right? Now if you spread them out like this, isn't it still true, this brain condition, that these two components have to balance out the weight? So I got 50 newtons and 50 newtons vertical to balance out 100 down. That's this condition. But look, I got a couple of right triangles. And what's the longest side of a right triangle? Hypotenuse. In which case, this free scale rating is more than half of the weight of whatever's hanging. Ah, more than half. Right? All right, got a shuffle. Tristan on fire on the top. Which has more mass? Kilogram of feathers, kilogram of iron. All right, same mass, same inertia, same weight, maybe different volumes, maybe different densities, but same mass. Yeah. All right, Harper, Amora, and Alex Soph. Stumpplaya, Tristan. How much does a 5 kilogram bag of bolts weigh? mg. Right, mass times gravity field. 5 times 10. 5 kilograms times 10 meters per second squared. 50 newtons. 50 newtons of weight. All right. For the win. For the win. 50 newtons, 20 newtons, same direction. What's the net force? Oh, yeah. Saddle them together, same direction. All right, to the podium. With the bronze. And Alex, oh, with the silver. Stuff like and they go. Tristan. Yeah. Next up. Was Jumbo and Amora. Yeah. Yeah. All right. Nice job, guys. I think I guys did best on that all day. All right, let's last few minutes here. Try to knock out a couple of text problems. Six puzzles. All right, number 60. Skating. We got Joyce and Upa. No, Efwa are skating. Joyce pushes Efwa with 5 newtons. And the mass of Efwa is 40 kilograms. What is Efwa's acceleration? Let's see, 60. So, Joyce and Efwa. Joyce and Efwa. Okay. Now, no, mass of Efwa is 40 kilograms. Okay. And there's this pushing. Oh, they're so about skates, right? Right. And there's a push of 5 newtons. That push goes 5 newtons. Guys, question: if let's suppose that Joyce is not on skates. Okay, so Joyce is grounded in the ground. Is that right? Pushes F1 with 5 newtons. Is there a reactive force back on Joyce? Is F1 pushing back on Joyce? What is that more than or less than 5 newtons, or the same, or the same? For every force there's an equal, opposite reactive force. Right. Now, what if Joyce is on skates? And you know what? Let's make the mass. I'm gonna make up something. Let's say the mass of Joyce is like 60 kilograms. Just make something up, right? And Joyce pushes F1 with 5 newtons, right? Right. What is the reactive force back on Joyce? Is it more than, less than, or the same as 5 newtons? The same. It's always the same, right? That's Newton's third law. All right, that was my own question. Their question is, what is the acceleration of F1? Well, would that be a net force on mass, right? You know, I can think of 3 forces on F1. F1 has a weight, F1 has a normal force, and also is being pushed by Joyce. But I bet those two verticals are canceling out, the weight and the normal force. Right here. If I do like a free body diagram, I got here. So mg is down, normal force is up. Those two cancel out. And here's the pushing force right here, the 5 newtons. Right. So I just care about 5 newtons acting on 40 kilograms. Could you guys call it like 1/8 of a meter per second squared? Right. Oh, and that would be the units, right? Meter per second squared. Right. Talk about acceleration. Guys, is meter per second squared? Is that the same thing as Newton per kilogram? Is that the same thing? It's the same thing, right? If you ever open up a physics textbook, it says Newton per kilogram. Same thing as meter per second squared. Right, number 82. Oh.
Pardon the interruption. If you ride bus 61 beginning tomorrow, you need to be at your bus stop in the morning at the appropriate time. Once again, if you ride bus 61 tomorrow, you need to be at your bus stop in the morning at the appropriate time.
All right, guys, let's get started on this one. So they told you the weight of a jet in newtons, that's the weight, is ready for takeoff. Its engines apply a constant thrust force of so many newtons. These are all in scientific notation. You guys see that, right? Right, 10 to 6 newtons. Right. How much runway will it need to reach its minimum takeoff speed in kilometers per hour? Right? Now, there's a bunch of little parts to this. I guess in that sense, it's kind of a complex problem, right? So here's big picture what we're doing. How much runway to reach a certain speed? That sounds kinematic. Does that sound kinematic? Right? And the only way to get there is, guys, what's the bridge between dynamics and kinematics? What variable? Acceleration. And the way we're getting acceleration, it's by Newton's second law. Here's the thrust force acting on the mass of the jet. Did they tell you exactly the mass of the jet? No, they told you the what? The weight of the jet. So maybe the first thing I want to do is actually find the mass of the jet. How do you go from weight to mass? Divided by gravity field, right? That should be weight divided by gravity field. I normally write m times g is equal to weight, right? Do a little rearrangement there. So they told you the weight of the jet's like 2.75 times 10 to the 6 newtons. So 10 to the 6, is that like a million? So it's like 2 million newtons divided by, I'm just going to call it 10 meters per second squared, right? So is the mass of the jet 2.75 times 10 to the 5th kilograms, right? Wouldn't it be? Right. There's the mass of the jet. So that was step 1. Okay. Step 2, let's find the acceleration of this jet. So that'd be the thrust force, right? It should be the net force, but that would be the thrust force, right? Because the weight and the normal force of that are balancing out. So the thrust force is the net force, right? Acting on the mass. So that's, what is it? 6.35 times 10 to the 6 newtons, acting on 2.75 times 10 to the 5th kilograms. 6.35 to the 6 divided by 2.75 to the 6. That's like 23 meters per second squared. Guys, is that like a solid like 2 G's, 2.5 G's about? Woo! If you're in that jet, you're really feeling the G's. You're feeling like 2.5 G's. All right, so that's halfway through the problem. We're gonna save the other half for another day. Yeah, there's a good pause point right there.